SwayamPrabha. Digital India. Educated India.
Welcome to the class of intelligent product design. So far what we have talked about, again I would like to recall step by step. Okay. So you have the design concept with you. Okay. Let us say I am just writing it here. Concept generation is the first thing in week 1 you have focused on. Then from there we have gone for the material selection. Okay. Once you have the concept, you have to use some material to build up on the concept, right. Then from material selection we have gone to two important aspects, that is called structure, and mechanism. Now once I do this, classically speaking, many products can be developed with this knowledge itself. Okay. I know, for example, we have seen that the table, a chair, a steam engine, okay, or something that is prior, let us say, the discovery of let us say the more complex systems like a complex machine, like let us say a lathe machine, or let us say further complex systems like aircrafts, okay, rockets, okay, today's automobile. Now here we cannot only keep ourselves happy by using only these three. Why is it so? It is because mechanisms and structures are generally designed keeping a typical working environment in mind. Okay. So the typical environment where the system is supposed to work most of the times, but the intelligent systems like us, let us say, we are typically designed to work on land. But let us say if somebody takes us to water, we still know how to swim. It is only a matter of learning. So, but we can do that. That means we have an adaptivity inside us, and adaptivity allows us to work under different environmental conditions. So from here our journey will start towards adaptivity. And how do we make things adaptive? Well, look at nature. There are two different strategies nature apply in order to make things adaptive. One strategy is that you simply have many generations. So there is a change of working environment. So there are some features that are good from your side, and then in the next generation through reproduction that is coming up, you select those people or population with the better features. But this way it works for millions of years. So this is a slower process, the process of evolution, reproduction and evolution. The other process of adaptivity is a quicker process. That means we are already having, the way I am telling that when we first learn, let us say, how to ride a bicycle, okay, we do not come up with the we do not born with the capacity to ride a bicycle. Okay. So we acquire that skill. How do we acquire that skill? The way we do is that we are equipped with certain sensors. What are these sensors? Well, we are equipped with some very interesting sensors like our eye. Okay. Eye gives us a sense of position, direction, etc. We also have a very interesting sensor on our two sides, and you may think that I am indicating the sound, but in terms of bicycle riding, that is not what is so important. Of course, you have to hear what are the other cars or something approaching, but the way it is important for bicycles is that the accelerometers that we have, that gives us a sense of stability, that okay, am I toppling or am I actually riding properly? And then that sensing that comes from stability sensing from the 2 ears is actually used as a feedback in terms of the driving of the bicycle. So, we use this type of sensors, and also you have to continuously rotate that the pedal and through the connecting rod in order to keep the bicycle moving, because bicycle is a fascinating example of a dynamically equilibrium system. So, those are the type of actuators, that is the use of our muscles. So, from here onwards we will look into the adaptivity, which will include the sensors, which will include the actuators, and finally the controllers. And when all these three things are there together, then we get something which is called embedded intelligence, okay, EI. This is embedded intelligence, and whatever we have learned so far can be considered as a part of physical intelligence or PI. So, it is the combination of this PI and AI which can make the system truly intelligent. Now, towards this direction, let us look into the sensors, okay. That is the focus today, that is introduction to the sensors. So, why do we need sensors? So, first important point is that to measure the system outputs for feedback control. I told you that if you take the bicycle example, then you need sensors to see in which direction you are heading, and also what is your tilting level, okay. So, you need a tilt sensing and you need a directional sensing. Sensors are also needed to measure system inputs, the desirable inputs, okay. The sensor tells us that are you driving slow or are you driving too fast, so that you are getting through sensors. To measure output signals for system monitoring, diagnosis, evaluation, parameter adjustment, supervisory control, all these things are also higher parts of how to use the sensory system. And then to measure input and output signal pairs for system testing and experimental modeling. This is particularly when the sensors are used for system identification. Let us say if there is a damage somewhere, fault identification, this is where also you will need sensors. Now, let us come to a case study of automobiles. Okay. If you look at an automobile, till 1960, the only intelligent electronic system in an automobile was actually radio. Engine systems were controlled mechanically, okay, using all those mechanisms that we have discussed, and conventional mechanically actuated ignition and fuel systems were, however, not precise enough to control the exhaust emission. So, 1960 to 70, the all sorts of electronic systems one by one in that decade started getting integrated in an automobile, like electronic ignition system, crankshaft position sensor, and also the camshaft position sensor, so that you can automatically ignite using these three systems. Then airflow rate sensor from the emission point of view, gas sensor, throttle position sensor, and a microcontroller to control all this process. So, that is how the automobile, and today many automobiles are there which has at least 10 to 12 microprocessors. Each one of them can be thought of a mini computer embedded in them. So, you can think of it that today's automobile is as good as a mechanical system as a electrical or a computer based system working together. So, late 1970, after all these things, then came a great development in automobiles. It is called ABS or anti-lock brake device. It actually senses the locking of wheels and modulate the hydraulic pressure to minimize the sliding. Then 1990, we get something which is called traction control system or TCS. It senses the slippage during acceleration and then modulate the power automatically to prevent the slipping of the vehicle. Today, we have much more advanced systems established in automobile like VDS, vehicle dynamics control, then millimeter wave radar technology with GPS based traffic updating. All these things are making an automobile more and more to a much more complex system. So, this is something the way the ABS works, that sensors at each of the 4 wheels are there, which senses the rotation of the wheel, and then if there is a too much of brake application, then it will stop rotating. The sensors immediately catch it that wheel is not rotating. ECU comes into action, it releases the brake line pressure and then the wheel turns again, and then ECU applies the pressure again and stops the rotation of the wheel, releases and go on and on. So, this release of the brake pressure and reapplication, so called pulsing of the brake pressure, happens 20 to 30 times per second. You can imagine how fast this is happening. Okay. So, this is something that needs a anti-lock braking system. What is the future of this kind of sensory systems? Okay. One of the things that we always say that for a great intelligent system example is a self-driving car, that the car itself drive. So, this Waymo is one of the example. Well, in terms of the integration of AI in cars, there are certain levels there. It is better to know about them. Like level 1 is called hands on. That means the autonomous system and the driver works together. Okay. So, example of the adaptive cruise control or ACC that many cars should be having. And then the hands off, that means level 2 of autonomy, where the autonomous system takes care of braking, acceleration and steering. You do not have to put your hand at all. Human contact is only necessary for emergency takeover. That is something that way the aircrafts already run, the autopilot. So, similar thing in the ground vehicle also has come up with a level 2 autonomy. Level 3 is even more autonomous, it is called eyes off. That means the driver can safely take his eye off and the vehicle will drive on its own, except at certain points if it has a doubt, it may call driver's attention for some decisions. Finally, level 4, which we have not reached yet, that is what is called minds off. No driving attention is at all required in the system. So, all the way this journey that we are doing to make a system fully autonomous to the level 4 autonomy, without sensors can we do it. So, this is where we will talk about that what is the source of this phenomenal advancement. Well, we will not call it just sensors. From today onwards, we will be more technical, we will call it transducers. Without transducers, we cannot do it. So, what is then a transducer? Fundamental mechanism of both sensing and actuation is actually the transformation of energy from one form to the other. Okay? We know that energy cannot be destroyed, but energy can be changed, and that is something that is taken advantage of in a transduction system. Now, multi-component transduction, for example, utilizes action at a distance behavior between multiple bodies. So, if you have a electromagnetic transduction, okay, typically you can have systems based on say Lorentz equation or Faraday's law. So, you can actually develop a transducer based on this, okay, something which let us say either sensing the rotation of a system or something which is actually changing the mechanical energy to electrical energy and such forms. Now, this can happen as an electromagnetic transduction, and similarly there can be electrostatic transduction also, which is based on Coulomb's law. Okay. Now, these are multi-component transductions. Then you have deformation based or solid state transduction, and this is something which is like based on say crystalline phase change. These are much more intelligent systems, we will talk about them, piezoelectric effect, shape memory alloys, magnetostrictive and electrostrictive materials, etc. So, these are actually something that is more high bandwidth type of a system in comparison to the multi-component transduction. Now, microscale systems are currently dominated by electrostatic and electromagnetic transductions, but we are soon transforming ourselves to the solid state transduction system. Now, let us say what is the basic component of a transducer. Well, what are the functional elements of them? The first point is of course a measurement system and that measurement medium, so which you are trying to measure, and then you are measuring a quantity in it, and then there is a primary sensing element there. That primary sensing element is changing this measured quantity in terms of a variable conversion element, then that goes to a variable manipulation element, then the data that is coming out of variable manipulation element goes to a data transmission element, and it goes to a data storage element, or otherwise it can directly go to a data presentation. This presented data finally comes to the observer. So many processes actually happens here. Okay. So, let us say for example, this system of a pressure gauge. Okay. So, measured quantity in the measurement medium is coming here. Okay. So, this is the primary sensing element is this piston part of it, and then the movement of the piston is not much. So, you have a conversion element you need. So, you need a mechanism here that will convert this motion into a rotational motion. So, you have a variable conversion element, and then you have to have a variable manipulation element. So, not only this mechanism is important, but you have to manipulate it, you have to keep it up to a certain distance, so that you can really see the angular displacements, etc. Then the data transmission element, that this data is transmitted to this particular scale, that is the data transmission element. Now, here after this you may have a data storage, you may not have. In this case it is a simple analog system, you do not have any data storage, and then you have a data presentation that is coming up here, and the observer is actually watching this data. Okay. So, observer is watching this data, that what is the reading of the system. So, all the sensors and the actuators have this particular direction of flow, the schematic representation of a sensor. So, you can have this system either something which is consuming energy from the environment itself, we will then call it a passive transducer, something which is good because you are not giving additional power, but bad because you are actually tampering the system. So, that it is both the sides are important here. So, the example is a board on pressure gauge, which is a passive transducer, and something in which you apply the power like a servo motor, in which you are applying an additional power, the auxiliary power system which is rotating the motor, and then you are measuring the changes. So, this is an active system. So, you can have a passive transducer, you can have an active transducer system. Now, we can have different type of sensor classifications. One, it can be based on the type of measurement, okay, that I am actually trying to measure. So, some is measuring a pressure, some is measuring a distance, some is measuring a tilting, depending on the measurement. Application field can be another. Okay. So, some is used let us say for optical purposes, all sorts of optical sensors. Then port model, I will come to the port model in a while. Conversion principle, that means definitely there will be some energy conversion. Is it between mechanical to electrical, or mechanical to optical, or mechanical to magnetic? These are conversion principles. Energy domain of the measurement, that is whether it is coming like a thermal energy transforming, or some other energy, light energy transforming, and also there can be based on certain thermodynamic considerations. But it is the port model which is most important in terms of creating an abstract description of a sensor. So, what is the concept of port? Well, energy enters or leaves the system always through a pair of terminals making up a port. That means, a port will be having a pair of terminal in it. Now, some group of sensors are direct sensor, which does not require any additional energy, generally like the passive sensors. So, these are what you call two port model or a 4 terminal model. Each port has 2 terminals. So, 4 terminal, or there are something in which there is a additional auxiliary power given to the system, and the modulation of that power is something that you are actually measuring. So, this is a 3-port system in which there is an input port and an output port. So, let us look into it graphically. So, this is a 2-port system. So, this is a 2-port system in which you have 2 terminal here and 2 terminal here. So, 1, 2, 3, 4. So, this is a 2-port system. So, you have input in one side and output in the other, and then you have 1, 2 and then 3, 4 and then 5, 6. You have 6 terminals, and maybe you are sending the measurement this way. So, this may be the measurement, and this may be for modulation or interrogation. This is the auxiliary port, and then this is the output. So, this is a 3-port system. So, 3-port and 2-port system you can clearly see. Now, what are the different energy conversion that can happen in a transducer? Well, we can create a matrix like if it is a radiant. So, this side is the input and this side is the output, okay, the horizontal way. And then if it is radiant energy, then it can be radiant energy transmitted to another radiant output, something like luminescence, or change to magnetic, photomagnetism, mechanical, radiation pressure, chemical, photochemical, electrical, photoconductivity. These are all example of radiant input getting transferred to radiant output. Then let us come to something which we know very easily, like mechanical input. Mechanical input creating thermal output, maybe in terms of friction heat. Creating magnetic field is magnetostriction. I will talk about it in the course of our discussions. Mechanical input creating a mechanical change in terms of a gear, mechanical output, or mechanical input creating a chemical change, maybe pressure induced reaction, or mechanical input creating an electrical field is like piezoelectricity. So, like that we have all these different types of patterns that is possible from the input to the output. Now, one way of actually clubbing all these things together is that how many latent information parameter input you are getting, the LIP input, and how many interrogating input you are getting. Now, we talk about different design variations of transducers, and one important concept here is this LIP, which is also known as the latent information parameters. And LIPs by default, all input ports are LIP ports. Now, LIP ports, the inputs are of 2 types. One is designed and controlled input, and another is you let the environment to give you the input, you do not design it. Okay. So, now if it is a design controlled input, let us say, and the interrogating input can be of 2 types. One is design controlled and another is environment controlled. So, if the input is design controlled and if the interrogating input is environment controlled, one type of sensor can come out of it, which is called direct sensor. Then, if it is environment controlled input and interrogating input is also environment control, you can get something which is called multiplying devices. So, like that you can have different types of such systems. One example of direct sensor is piezoaccelerometer. One example of multiplying devices is called Hall sensor. Okay. And one example of modulating sensor is called strain gauge. So, depending on how the input output relationship is and what is the interrogation happening, you can have different types of designs of the transducers. Now, classically we can define the transducer with the help of 3 indices which are very similar to what you call the Miller indices. So, similar to the Miller indices, we will consider that there is a 3, I told you already that it can be a 2-port or a 3-port system. Okay. Now, here we have used certain abbreviations. Okay. For example, this is TH, and EL or MA and EL. Okay. And you see, if the more common description is if it is a 3-port system. And so, this TH, EL and MS and all these things you have to just go back and see it here. TH is for thermal, RA is for radiation, MA is magnetic and ME is mechanical, CH is chemical, EL is electrical. Okay. So, this if you keep in your mind, then you can see it here like a thermocouple. It has temperature or the heat as an input. So, thermal energy and then it is converting it to an electrical output directly. So, EL, and there is no interrogation medium, that is why this is 0. This is what is called a thermocouple in a Miller index. Okay. So, I can write it as, say, one index is input port, okay, and another we can call it as interrogation port, and this one is the output. So, this is the first quantity 1, this is the second and this is the third. Okay. Now, you can see, let us say LED. LED we always know it is a light emitting light emission detector. So, input is what? Input can be in terms of this system, it depends on the type of input actually. So, you can in fact interchange between the two. So, you can have a radiation as an input and electricity as the output, but definitely there is no sort of interrogation medium there. And then there are certain things like, let us say, the Hall sensor. Hall sensor has a magnetic field as an input and then you have one electric field that you are applying and the output also as electric field. Okay. So, you can have electric field as an output and interrogation medium also as electric field that you need. Now, finally, there are these binary sensors. Binary sensors are like switches. So, it cannot give any in between value, it can only give that whether it is on or off. So, the 0 or 1. Okay. Hall sensors are, for example, binary sensors. So, certain sensors are designed in a way that they are binary sensors, they are very cheap, but they just work like a switch. Now, fundamental measurements are only 4. What are these fundamental measurements? First one is the length, of course, and we know the SI unit is meter, and that is the distance travelled by light in vacuum during a time of this much of second. That is what is the definition, that is light travelling in vacuum in a certain second is defined as the meter. Then the another fundamental measurement is time, and the time is, definition of time is continuously changing. Currently, it is this many number of times the period of vibration of radiation from a cesium atom that defines the second. Then mass, and currently it is kilogram, and it is defined at the mass of a specific type of platinum iridium alloy cylinder, which is kept at the International Bureau of Weights and Measures at Service, France. And then based on this, the reason of choosing this is that platinum iridium is an unusually stable alloy. Based on this, we keep the unit of mass. Another fundamental unit is actually the temperature, and Kelvin has defined this as 1 over 273.16 of the thermodynamic temperature of the triple point of water. So, these 4, length, time, mass and temperature, are the most fundamental measurements that we always measure in a system. Now, out of these, the most interesting one is the time. The evolution of horology, that is the measurement of time, if you look at it, you would see that there was a time when people have used different types of balance clocks, then they use different types of pendulum based system like Hygiene's famous system. Then from there the chronometers or compensators, then it becomes the pendulum free systems based on the potential energy of the torsional springs, and then the quartz crystals, the first atomic clock, then the cesium atomic clock. So, now most of the very good timekeeping machines are all based on cesium atomic clock. Now, once you know the time, then you need to measure two important things from engineering application point of view, and that is the motion sensing and the force sensing. This is where we will end today's discussion. So, motion sensing can be in terms of displacement sensing of various types like position, distance, range, proximity, level, angular sensor, encoder, tilt sensor, tachometer, vibration sensors. These are all different form of displacement sensing. So, this is one way of sensing motion. Then you have velocity sensing, then you have acceleration sensing and jerk and impact sensing. So, these are all related to motion sensing. The other type of fundamental sensors are required for force sensing, like the pressure sensing, force itself, torque sensing, load cell, strain gauge, touch sensing and tactile sensing. So, these two major groups of sensors are what is going to dominate in our choice of sensors in terms of giving us feedbacks from certain mechanisms, from certain structures, and then make a system adaptive. In the next lecture, we will see more details about the sensors. Thank you.